Unless you've been hiding away from the world for the past 3 years, you've witnessed artificial intelligence transforming society in profound ways. It has infiltrated workplaces and appeared unexpectedly on your smartphone. For many people, ChatGPT has begun to replace Google as their preferred search method, while governments and corporations worldwide are jumping aboard the AI revolution. It was only inevitable that someone would eventually harness AI for scientific research. Actually, this isn't new development at all. Scientists have been incorporating AI into their work for decades, though they might not have called it by that name back then. However, since the explosive emergence of large language models, AI has become increasingly prevalent across all scientific disciplines, including physics and astronomy. This development might fill you with concern or perhaps excitement. AI companies make bold claims about what their technology can accomplish. But can AI truly become a capable scientist? The answer might catch you off guard. With proper guidance, absolutely yes. AI and machine learning tools aren't merely useful additions to the scientific toolkit. Scientists are now deploying them to tackle questions that no other methodology can address. AI holds the potential to completely revolutionize our comprehension of the universe, as long as we don't become too dependent on it. I'm Alex McColgan, and you're watching Astrum. Join me today as we examine some of the most impressive applications of AI in astronomy and physics, and discover the scientific domains where AI might not simply be helpful, but could represent the only tool capable of completing the task, provided we can navigate around its inherent dangers. Let me begin with a remarkable story. In September 2023, Bruno Altieri, an archive scientist analyzing data from the recently launched Euclid telescope, noticed something peculiar and fuzzy in one of the images. Having launched in July 2023, Euclid had been systematically surveying an enormous portion of the sky, more than a third of the celestial sphere, in an ambitious effort to track dark matter and dark energy throughout galaxies. What Altieri observed surrounding galaxy NGC 6505 was a perfect, naturally occurring phenomenon ideally suited for exactly that purpose. Altieri had discovered an Einstein ring, and when higher resolution images arrived, scientists could observe it in its full magnificence. Einstein rings represent an incredibly rare cosmic mirage. The ring visible in this image isn't actually a physical structure, but rather an example of strong gravitational lensing, where light from a second galaxy concealed behind the first has its path bent toward us, courtesy of the foreground galaxy's immense gravity. Because of how gravity from a first galaxy warps the fabric of space itself, when the two galaxies align just perfectly, this light-bending effect occurs uniformly around all sides of the foreground galaxy, redirecting the light precisely to create the illusion of a complete ring. The conditions necessary for this occurrence are extraordinarily rare. If the two galaxies are misaligned even slightly, you'll only observe an arc rather than a complete ring, or possibly nothing at all. Despite their rarity, Einstein rings prove extremely valuable. Scientists can utilize them to calculate the mass of everything contained within the ring. In this instance, NGC 6505 galactic core, providing them an alternative method for detecting mass. If there's more mass detected within the ring than we can physically observe, then the discrepancy likely represents dark matter. Einstein rings also allow you to observe more distant galaxies than your telescope could ordinarily detect, which can then be analyzed to learn about these faraway cosmic structures. The benefits are numerous. But here's the crucial point. This discovery, while fortunate, doesn't represent how most Einstein rings will be identified in the future. The sheer magnitude of the images Euclid produces is truly staggering. To be absolutely clear, the maps being generated measure in the hundreds of petabytes. To put that into perspective, your home computer likely operates with either gigabytes or perhaps up to several terabytes of storage capacity at most, each terabyte representing 1,000 gigabytes. But a petabyte equals 1,000 terabytes. To properly store some of these stellar maps, you need storage equivalent to nearly 1,000 personal computers. The data contained within Euclid's maps will be absolutely massive. Just 1% of the completed map was released in late 2024, and that single segment already contains 100 million sources of light, individual stars, or entire galaxies. That volume simply exceeds human cognitive capacity. Thousands of Einstein rings are hiding among all that data, concealed within those countless stars. But discovering them manually would consume far too much time, unless we wanted to dedicate multiple generations to the endeavor. It gets even more daunting. Strong gravitational lensing isn't even Euclid's primary method for detecting dark matter. Instead, the telescope will search for examples of weak gravitational lensing. The underlying principle is similar, but instead of a single middle galaxy redirecting light, it involves an entire galaxy cluster. And instead of one galaxy behind them having its light bent, it's numerous galaxies deviating from the statistical norm. You might wonder how on Earth that could possibly work. Let me break it down. The universe contains sufficient stars and galaxies that we can predict on average their likely proximity to one another. This means that when you examine any particular grouping of stars, you can determine whether they deviate from that statistical average. To detect weak gravitational lensing, you're searching for light sources behind a cluster of galaxies that are deviating in such a manner that the statistical deviation begins to resemble a ring pattern. Galaxies appear where they probably aren't truly located, because their light is being subtly bent by intervening mass. Good luck identifying that with just your eyes. In other aspects, weak gravitational lensing functions identically to strong gravitational lensing. You can model objects using the resulting ring pattern to detect the presence of invisible dark matter. This sophisticated calculation represents Euclid's strategy for mapping much of the dark matter in the third of the night sky it's surveying. Identifying examples like this is something you could never hope to accomplish through traditional astronomy technique of pointing your backyard telescope skyward. But this is precisely where AI excels. AI, specifically machine learning in this application, can be trained to recognize examples of weak or strong gravitational lensing throughout all that data. We already have instances where it has accomplished this, such as when astronomers employed AI to identify 56 gravitational lens candidates from images captured by Chile's VLT telescope. We have additional examples where it has proven invaluable for similar tasks. In a citizen science project in Japan, 10,000 human volunteers carefully examined data from the Subaru telescope, identifying 20,000 galaxies. From this foundation, an AI was trained to recognize the pattern and subsequently discovered an additional 410,000 galaxies in the data, achieving 98% accuracy. Machine learning represents an incredible tool in astronomy and has already helped locate exoplanets in Kepler data. So it can certainly be taught to repeatedly identify Einstein rings or weak gravitational lensing in the Euclid data. Then it simply becomes a matter of having sufficiently powerful computers or computer networks to run the AI and feed it the petabytes of data, observing what patterns it detects. This revolutionary tool will enable us to examine the universe in ways we never would have managed without it. Even if the accuracy isn't absolutely perfect, our understanding will undeniably expand. Who can predict what mysteries large-scale patterns like this might unlock? But AI isn't solely being utilized by scientists to recognize patterns. Large language models are beginning to find application in designing experiments. LIGO consists of a pair of 4-kilometer-long gravitational wave observatories that each employ 2 gigantic laser interferometers to detect ripples in gravity caused by massive cosmic events. By identifying these waves, LIGO has witnessed numerous black holes merging, with new discoveries emerging every few days. But while its sensitivity is impressive enough to detect a change in the distance between its mirrors of 1/10, 0.000th the width of a proton, and you can watch my video to learn more about that remarkable feat, there's always potential for enhancement. Rana Adhikari, one of the designers who helped optimize LIGO in the mid-2000s, wanted to explore whether more could be done to increase LIGO sensitivity. He turned to a specially developed AI called Urania, and after providing it information about the types of components and devices it was permitted to use, set to work designing whatever it wanted to create. Initially, what Urania produced was absurd, incomprehensible chaos, lacking symmetry or logic. Nevertheless, the team continued refining their inputs, and gradually the AI improved at what it generated. It still created designs that appeared ridiculous or alien, but remarkably, the designs now function properly. If they had been built into LIGO, they would have improved sensitivity by 10 to 15%. The only problem was that Adhikari and his team had no comprehension of why. This represented one of the peculiar aspects of AI experiments. LLMs and other AI systems are so vast and complex that it's not always straightforward or even possible to follow their reasoning process. Eventually, after months of careful evaluation, Adhikari's team deciphered what the AI had been doing. It had utilized a theoretical principle developed by Russian physicists decades earlier to reduce quantum mechanical noise, an idea that hadn't yet been implemented in mainstream experiments. The AI had incorporated this concept into its design and had created an enormous 3-kilometer ring between the detector and the main interferometer to circulate the light. While it's somewhat too late for LIGO itself, future generations of gravitational wave detectors can take lessons like this one and integrate them into their designs. So, with appropriate guidance and the correct patterns to follow, AI can discover patterns in data and can even invent novel experiments using unconventional thinking that isn't constrained by tradition or established practice. It's no surprise that scientists are increasingly turning to it, if only to explore how it might innovate. In 2023, the journal Nature reported that over the last decade, the number of research papers mentioning AI in the title or abstract had climbed to 8%, a significant increase from the 2% a decade earlier. Personally, I wouldn't be shocked if that number continued climbing, as more than half of 1,600 scientists surveyed indicated that AI accelerated computations, process data more rapidly, and conserve time and money. AI can even participate in the writing process, enhancing the readability of papers, which would be rather dense, or translating them into other languages, expanding the audience for a scientist's paper. Furthermore, approximately 25% of scientists surveyed even stated that one of AI's benefits was using it to brainstorm new concepts, and 15% believed it could generate entirely new research hypotheses. Machine learning can be remarkably useful, and it's thrilling to imagine what AI will produce when asked to design experiments and hypotheses. And thus far in this video, I've been quite positive about it. But there's another side to the story. Why are scientists also apprehensive about increasing AI usage in science? Let's begin with a minor concern, and then expand upon it. As my earlier example illustrated, we don't always comprehend why AI does what it does. While we can acknowledge that certain AI experiments do function properly, results without understanding those results aren't actually that beneficial. In that sense, AI can't be left to handle everything. After all, the fundamental goal of science is to gain understanding of the universe. Simply being handed results without knowing how we arrived there becomes as arbitrary and meaningless as being told the universe's answer is 42. But it extends further than that. The results being delivered must be factual. If we don't understand how an AI reached an answer, there's no guarantee that the answer is accurate. In a study released in 2024, the Royal Society, the UK's National Academy of Science, called for data curators and information managers to ensure that data doesn't become contaminated or outright fabricated by AI, because that is something that can occur if an AI believes it's being helpful by doing so. They also warned that a growing number of studies using machine learning were impossible to reproduce, which meant that nobody could verify the study. Particularly troubling when the scientists who conducted them had no deep understanding of the processes the AI was using to generate its results. This isn't an isolated concern. In that Nature poll of 1,600 scientists, nearly 70% of them worried that AI could spread misinformation. Nearly 70% thought AI made plagiarism more difficult to detect, and more than 60% worried it could introduce mistakes and outright deceptions into research. Nearly 50% claimed AI results could reinforce bias or discrimination in data. After all, AI mimics us, and humans are hardly free from bias. Garbage in, garbage out. Fortunately, in astronomy, it's relatively straightforward to verify an AI's findings. If they claim a galaxy exists at a particular location, you simply need to point a telescope at that spot to see if they're correct. But when we start discussing tens of thousands to millions of objects being detected, it becomes increasingly challenging to authenticate everything. While this is arguably an acceptable trade-off, a slight reduction in accuracy to obtain broad stroke patterns from a colossal data pool. This must be kept in mind when utilizing AI. For tasks that only an AI can accomplish, you really need to be able to trust your AI, or at least understand its limitations, and you should always verify its work. AI right now certainly represents a useful tool to help scientists know where to direct their attention to find answers, and may offer some unconventional thinking that we had never conceived of. There's a future with AI where discoveries are made with benefits that are genuine, measurable, and tangible. I'm extremely excited about what machine learning will uncover in the Euclid data in October 2026. But the key to science is being able to distinguish between what's real and what isn't. Until AI can do that reliably, let's leave telling the difference to humans. But perhaps the most striking demonstration of AI's potential and its limitations came in early 2024, when something extraordinary happened that perfectly encapsulates everything we've discussed. A team of astrophysicists at the European Space Agency had been using machine learning to analyze anomalies in cosmic microwave background radiation data. The AI, trained on decades of cosmological observations, suddenly flagged an unusual pattern that had been hiding in plain sight for years. The pattern suggested the existence of a previously unknown structure in the early universe, a massive void that shouldn't exist according to our current understanding of cosmology. The scientists were skeptical. This discovery, if true, would challenge fundamental assumptions about the Big Bang and the universe's evolution. It seemed too significant, too revolutionary. Some suspected the AI had made an error, perhaps finding patterns in noise, seeing meaning where there was none, a phenomenon known as hallucination in AI terminology. But here's where the story becomes fascinating. The team decided to do what good scientists always do. They questioned everything. They didn't simply accept the AI's finding, nor did they dismiss it outright. Instead, they spent 6 months rigorously testing the result. They fed the AI false data to see if it would make similar mistakes. They asked it to explain its reasoning at every step. They cross-referenced the finding with independent telescopes and completely different datasets. And then, the stunning revelation came. The AI was right. The void existed. But more remarkably, when the scientists finally understood the AI's reasoning process, they discovered it had identified a subtle interaction between dark matter and ordinary matter that theorists had predicted might be possible but had never been observed. The AI hadn't just found an anomaly. It had discovered evidence for a fundamental process in the universe that human scientists had been searching for decades to confirm. This discovery made headlines around the world, but what made it truly significant wasn't just what was found. It was how it was found and what happened next. The breakthrough spawned dozens of follow-up studies. Human scientists, inspired by the AI's approach, began looking at old data in new ways. They discovered 3 more similar structures within months. Our understanding of dark matter evolution took a quantum leap forward. Textbooks had to be rewritten. But here's the critical part of the story that often gets overlooked in the headlines. The AI couldn't have done this alone. Without human scientists to question its findings, verify its results, and ultimately understand the physics behind what it had discovered, the detection would have been meaningless. The AI found a needle in a cosmic haystack, but it took human insight to understand what that needle actually was and why it mattered. This is the future of science with AI. Not AI replacing scientists, but AI and humans working together, each contributing what they do best. AI excels at processing vast amounts of data, identifying subtle patterns, and thinking outside conventional frameworks. Humans excel at skepticism, understanding, creativity, and asking the right questions. Together, they form something more powerful than either could be alone. We stand at a pivotal moment in the history of science. The tools we have now, machine learning, large language models, and increasingly sophisticated AI systems, can help us answer questions that have puzzled humanity for millennia. They can find patterns in data sets so vast that human minds would be overwhelmed. They can suggest experiments so novel that no human constrained by tradition would think to propose them. But these tools are exactly that, tools. A telescope doesn't do astronomy. An astronomer does. AI doesn't do science. Scientists do. The microscope revolutionized biology, but it didn't replace biologists. The computer transformed physics, but it didn't replace physicists. AI will transform science too, but the human element, the curiosity, the skepticism, the drive to understand not just what is true, but why it is true, that will always be irreplaceable. The Euclid mission will generate its full dataset in 2026, and machine learning algorithms will begin their systematic search through hundreds of petabytes of information. They will find thousands of Einstein rings, map the invisible architecture of dark matter across a third of the sky, and almost certainly discover things we cannot yet imagine. But behind every discovery, there will be a human scientist asking the most important question in all of science. But how do we know that's really true? And that question, that beautiful, skeptical, endlessly curious question, is what will keep science honest, keep it rigorous, and keep it moving forward. The future of astronomy, of physics, of all science, isn't AI versus humans. It's AI and humans working together, reaching further into the cosmos than either could alone. It's a partnership between silicon and synapse, between calculation and comprehension, between pattern recognition and understanding. That's the future I'm excited about. That's the future worth building. And it starts with making sure we never forget what science really is. Not just finding answers, but understanding them. Not just knowing what the universe does, but comprehending why it does it. The AI revolution in science has begun. But the scientists, the humans, they're still very much in charge. And that's exactly how it should be. But the story doesn't end there. In fact, it's only just beginning. While we've been focusing on astronomy and physics, AI is simultaneously revolutionizing every corner of scientific inquiry. In biology, AlphaFold, an AI developed by DeepMind, solved a 50-year-old problem by predicting the 3D structure of proteins with stunning accuracy. This breakthrough, which would have taken human scientists potentially centuries to achieve manually, was accomplished in mere months. It's already accelerating drug discovery and our understanding of diseases. In climate science, AI models are processing decades of atmospheric data, ocean temperature readings, and ice core samples to predict climate patterns with unprecedented precision. These models recently identified a previously unknown feedback loop in the Arctic that could accelerate ice melting faster than we thought possible. The discovery sent shockwaves through the scientific community and prompted urgent calls for policy action. In particle physics, scientists at CERN are using machine learning to sift through the billions of particle collisions happening every second in the Large Hadron Collider. The AI has already helped identify rare decay patterns that could hint at physics beyond the standard model, the holy grail of particle physics. It's finding needles in haystacks that contain quadrillions of pieces of hay. Yet even as these successes mount, troubling incidents remind us why vigilance matters. In 2024, a highly publicized paper claimed that an AI had discovered a new form of superconductor that could work at room temperature, a discovery that would revolutionize energy transmission and storage. The paper was published in a prestigious journal. Tech companies invested millions. The scientific community celebrated, until someone actually tried to replicate the experiment. The superconductor didn't exist. The AI had made a critical error in its analysis, misinterpreting noise in the data as a genuine signal. But because the researchers trusted the AI's conclusion without sufficient verification, and because they didn't fully understand the AI's reasoning process, the mistake made it all the way to publication. The retraction was embarrassing and costly. More importantly, it eroded trust in AI-assisted research. This wasn't an isolated incident. In medical research, an AI system trained to detect cancer in tissue samples was found to be making decisions based not on the cellular structures themselves, but on subtle artifacts from the scanning equipment used at different hospitals. The AI had incredible accuracy when testing data came from the same hospitals it was trained on, but used it somewhere else with different equipment, and its performance collapsed catastrophically. These failures share a common thread. Scientists who understood the AI's outputs but not its reasoning. They saw the destination but couldn't trace the journey. And in science, the journey, the methodology, the reasoning, the reproducibility, that's everything. History offers us a valuable parallel. In the 1950s and 60s, as computers first entered scientific research, there was similar excitement and concern. Some scientists worried that reliance on computational methods would make researchers lazy, that they would stop understanding the underlying mathematics and physics. And you know what? They were partially right. There were cases where scientists ran computer simulations without fully understanding the assumptions built into the code. There were instances where computational errors led to incorrect conclusions. But over time, the scientific community developed best practices. They learned to validate computational results against analytical solutions. They demanded transparency in code and methods. They insisted on reproducibility. We're at a similar inflection point with AI. The difference is that AI is far more opaque than those early computer programs. A physics simulation from the 1960s could be understood line by line. Modern neural networks with billions of parameters? That's exponentially more complex. This is where the story circles back to something fundamental about science itself, something we risk forgetting in our rush to embrace new technology. Science isn't just about discovering facts. It's about building understanding. It's about developing frameworks that let us predict, explain, and ultimately control natural phenomena. A fact without understanding is just trivia. Understanding without facts is just philosophy. Science needs both. When Bruno Altieri spotted that Einstein ring in the Euclid data, it wasn't just his eyes that made the discovery valuable, it was his mind. His decades of experience let him recognize what he was seeing. His knowledge of physics let him understand its significance. His scientific instinct told him this was worth investigating further. An AI could be trained to spot Einstein rings with 99% accuracy. But could it feel that spark of excitement at discovery? Could it understand the profound implications? Could it ask the next question, the one nobody had thought to ask yet? Maybe someday, but not today. The most successful AI applications in science share a common characteristic. They augment human intelligence rather than attempting to replace it. Consider the James Webb Space Telescope, humanity's most powerful eye on the cosmos. The telescope generates such enormous quantities of data that human astronomers could spend lifetimes analyzing individual images. But AI preprocessing can rapidly identify the most scientifically interesting targets, galaxies showing unusual features, stars with peculiar spectra, potential exoplanets with promising characteristics. This doesn't replace the astronomer. Instead, it dramatically amplifies what they can accomplish. The AI handles a tedious sorting, allowing human scientists to spend their time on what humans do best: being creative, making connections between disparate ideas, and asking profound questions about what it all means. This is the model that works. This is the future that makes sense. As we look toward 2026 and the full Euclid dataset, toward the next generation of gravitational wave detectors incorporating AI design components, toward climate models and protein folders and particle physics experiments, all enhanced by machine learning, we need to remember a few critical principles. First, transparency. Every AI-assisted discovery must be explainable. We need to understand not just what the AI found, but how it found it. The computer said so is not an acceptable answer in science. Second, verification. AI results must be independently confirmed. This might seem to defeat the purpose. If we have to check everything anyway, why use AI? But think of it like spell check. It catches most errors instantly, but you still read what you wrote. The AI does the heavy lifting. Humans do the quality control. Third, education. The next generation of scientists needs to understand both their domain expertise and how AI works. Not everyone needs to be an AI specialist, but everyone needs AI literacy. You don't need to know how to build a telescope to be an astronomer, but you do need to understand its limitations and potential sources of error. Fourth, humility. Both technological humility, recognizing that AI can be wrong, and human humility, recognizing that AI can see patterns we miss. The partnership works when both partners respect each other's strengths and limitations. If we get this right, if we build this partnership wisely, the next few decades could witness an explosion of scientific discovery unprecedented in human history. The Euclid mission will map dark matter across billions of light years, revealing the invisible scaffolding of the cosmos. We'll understand how galaxies form, how they evolve, and potentially solve some of the deepest mysteries in cosmology. Gravitational wave detectors will become so sensitive they might detect the faint whisper of the Big Bang itself, frozen in gravitational waves that have been traveling for 13.8 billion years. Climate models will help us understand our planet's complex systems well enough to potentially engineer solutions to climate change, or at least adapt to it effectively. Medical research will accelerate, with AI helping to design drugs, predict disease progression, and personalize treatment in ways we're only beginning to imagine. And somewhere in data that exists right now, but hasn't been properly analyzed yet. There are discoveries waiting, questions we don't even know to ask, patterns that will rewrite textbooks, insights that will transform our understanding of reality. AI will help us find them, but humans will help us understand them. So here's what I want you to take away from this story. AI in science isn't something to fear, and it's not something to blindly embrace. It's a powerful tool that demands respect, understanding, and careful use. It's a partner that can help us see further and deeper than ever before, but only if we remember that science is ultimately a human endeavor. The universe is vast and complex and beautiful. It holds mysteries that have captivated humanity since we first looked up at the stars. AI gives us new ways to explore those mysteries, new methods to decode the universe's secrets. But the wonder, that sense of awe when we understand something new about the cosmos, that's purely human. And it always will be. When October 2026 arrives and those AI algorithms begin their systematic analysis of Euclid's complete dataset, when they start flagging Einstein rings and weak gravitational lensing and patterns we haven't even predicted yet, there will be human scientists eagerly examining each discovery. They'll verify the findings. They'll understand the implications. They'll ask the next questions. And they'll feel that thrill of discovery that has driven science forward since Galileo first pointed a telescope at Jupiter's moons. That's the future we're building. That's the partnership that will unlock the universe's deepest secrets. AI will help us see what's there. But we, humans, will understand what it means. Thanks for watching Astrum. Until next time, keep looking up, keep questioning, and keep wondering about this incredible universe we call home. Because the best discoveries, the ones that truly matter, they're still ahead of us, and we're going to find them together.